Look around at the machines defining our era. From the drones lifting out of our cities to the electric cars hitting 60 in under 2 seconds, these vehicles rely on a hidden, silent force driving them forward. My name is Akmal, and as a BND student at UTM, I've spent a lot of time looking under the hood for my portfolio. My specific focus is on the core technology making all this movement possible: motors and generators. To understand how far we've come, we have to look at where we started. Early electric motors were heavy, iron-clad machines wrapped in thick copper coils, designed to harness raw electromagnetic power. The modern hyper-efficient vehicles we rely on today are still entirely bound by the physics established in those early iterations. Before we can push the boundaries of speed, we first have to master the unbreakable rules written over a century ago. Those rules are defined by Maxwell's equations. Think of them as the strict, non-negotiable boundaries that every electrical engineer has to work within. The physics boils down to two interactions. An electric current running through a wire generates a localized magnetic field around it. Conversely, passing a changing magnetic field over a wire induces a voltage. This endless loop makes every motor spin. Here lies the problem. If we are trapped inside this closed loop of physics, how do we pull exponentially more power for modern heavy-duty applications without violating the laws of the universe? For decades, the industry answered that question by relying on a standard design known as the radial motor. We've actually been trying to put these into vehicles for a long time. Even the earliest electric cars were weighed down by massive chassis just to support the physical bulk required by these traditional power setups. Look at the geometry here. A radial motor is shaped like a long cylinder. Inside, the magnetic forces push radially outward from the spinning axis in the center. Because of that specific spatial layout, if you want more power, your only option is to build a larger motor. You have to extend the cylinder to make it longer, or expand it to make it wider. That creates a harsh bottleneck. Adding power means adding unacceptable weight, destroying the exact efficiency you need to keep a drone in the air, or make a sports car agile. Recently, the industry found a way out of this trap with the axial flux permanent magnet motor. Instead of fighting physics, engineers changed the shape. Imagine taking that long radial cylinder and squashing it into a flat disc, or a pancake. This geometric change flips the physics. Now the magnetic force flows completely parallel to the central spinning axis. That single spatial adjustment packs an incredible punch. It allows us to extract a massive increase in torque and shear power out of a much lighter, significantly smaller motor frame. We didn't change the laws of electromagnetism, we optimized the space they operate in. And that clever spatial efficiency is exactly why axial flux motors have taken over the heavy-duty drone and high-performance EV markets. Looking at this shift from the outside, there is a much larger lesson here about how human innovation actually works. Engineers achieved these significant gains in power and efficiency without discovering a new supermaterial or a different set of physical laws. The fundamental equations of electromagnetism stayed constant. This proves that engineering genius is often found in creatively rethinking the geometry of existing physics. By identifying that the cylindrical shape itself was the limiting factor, a simple spatial pivot unlocked power that was always there. Innovation is primarily an act of perspective. It's the ability to find entirely new spatial arrangements within the strict rules we already know. For me, this realization clarifies how I want to approach my own work at UTM. Moving forward, I plan to keep exploring this specific motor concept. I'll be diving deep into academic journals and putting these theories to the test with small-scale experiments using my Arduino setup. Because understanding the theory is only half the job. The real progress happens when you start wiring components on a breadboard and getting your hands dirty with the hardware. Major engineering breakthroughs are often hidden in plain sight, waiting for someone to look at an old problem from a completely different angle. Thanks for watching.